Okay, good morning, everyone. We are almost starting this webinar, but let's give the right time to a participant to connect to the webinar, and then we can start. Yeah, the number is slowly rising, so let's wait for another minute to have, let's say, the good number of participants. The number is rising. We are more than 20. Let's wait a bit, and then I do believe that we can start. Okay, so good morning, everyone. I'm Elisa Furlan. I'm a scientist at the Foundation Euro-Mediterranean Center on Climate Change. I'm currently engaged in the division on risk assessment and adaptation strategies. But today I'm really pleased to welcome you to all of you to this webinar, and especially to present you my colleague Melissa Latella, that is going to present during this webinar. Melissa is a researcher at the CMCC, at the Euro-Mediterranean Center on Climate Change Foundation, and especially she's engaged in the Institute for Climate Resilience, and she's working within the brand new division on soil and water system. With a PhD in civil and environmental engineering from the Polytechnic of Turin, her research focuses on cutting-edge solutions for soil erosion modeling, integrating Earth observation system and AI model for advancing the knowledge into riparian vegetation monitoring. Her main research interests are the dynamic interaction between sediment, water, and vegetation across river, watershed, and coast, leveraging these two right to fill the gap in the knowledge. Indeed, in her presentation today in the webinar, she will tell us more about ecomorphodynamic system, focusing on dune and riparian corridors. Within this system, there is still incomplete knowledge on the responses to the external driver and the management strategies. So Melissa, in her research and her collaboration with CMCC, is trying to fill this knowledge gap. And this seminar will show us how remote sensing can bridge monitoring to modeling ecomorphodynamic system by providing results, outcomes, and modeling approaches from 4 practical examples that are located within fluvial and coastal environment. So, but before going into the webinar and Melissa presentation, let me also introduce you the Foundation Euro-Mediterranean Center on Climate Change. That is a research foundation which mainly focuses on climate science and the investigation and the modeling of our climate system. Our main mission is understanding the interaction and interplay among climate change, society, and environmental system, to provide reliable results, tools, methodological approach that can support science-based policies, plans, and adaptation planning measures. So basically, we want to move from models to solution and be supporting the policymaker in their task of let's say implementing measures to adapt to climate change. But how to respond to this crucial need? Our research is interdisciplinary and is articulated across different research institutes. So this is why we recognize 3 interdisciplinary research institutes, 4 strategic programs, and then center, let's say. These are the research institutes that are related to the Institute for the Investigation of the Earth System and Prediction, so mainly dedicated to predictive and modeling tools. The Institute for Climate Resilience, that is the institute where me and Melissa are engaged, which create data-driven digital representation of the Earth system component and also support risk assessment modeling and adaptation planning. And then the third institute, which relates to the European Institute on Economics and the Environment. We also recognize four strategic programs that, as you can see from this slide, they are quite articulated, and they span from the focus on the global cost as the new frontier for climate adaptation in the investigation and the modeling of the interaction between the lands interface, to a strategic program which specifically focus on leveraging and integrating AI-based and machine learning within the modeling chain. And finally, we recognize within this big framework of interdisciplinary research, CMCC Center with the High Performance Computing Center, that is a, let's say, computational infrastructure and facility that is completely dedicated to the modeling investigation of the climate system. Then there is the Center on the Advanced Digital Innovation, and finally, the Center on Advanced Training and Education. So this is CMCC in a nutshell, but how this webinar is going to work. So basically your audio and video are deactivated by default. So if you want to jump in, step in into the discussion and pose your question to Melissa at the end of her presentation, you can use the Q&A session within the webinar. So I will say that everything is ready, Melissa. So I leave you the floor, and for all the other participants, enjoy this webinar and Melissa presentation. And thank you.
Okay, I'll share my screen. Okay, do you see my presentation?
Yeah, sure.
Okay, perfect. Thank you everyone for being here, and thank you Elisa for your introduction. Today I will talk about ecomorphodynamic systems, and I will talk a little bit about the challenges we have for their studying and management. And I will show with some example from my research activity how I try to solve, at least in part, some of these challenges. And I will talk about 4 applications in my research. The first one will be a little bit larger, and then other 3. So let's start. Ecomorphodynamic systems are shaped by the continuous adjustments of landforms and living organisms. Here I reported 2 examples of ecomorphodynamic systems in which I worked. The first one is vegetated coastal dunes, where the dune formation and evolution is triggered and moderated by the continuous interaction between vegetation, sediments, and water fluctuations, although also other factors contribute, as you can see in this diagram. Also, I worked in riparian corridors, and generally when we talk about the evolution of riverscapes, ecomorphodynamics is simplified into the so-called ecomorphodynamic triad, which is composed by sediments, vegetation, and water flows. Coastal dunes have a worldwide presence. You can see in this map how they occupy large part of the global coast. But also riparian corridors are widespread, as you can see on the right panel. Although riparian and coastal environments might appear as separated, as disconnected from each other, actually they are part of a unique continuum from source to sea. And along this continuum, they provide crucial ecosystem services for our communities. For instance, they support high biodiversity, or they protect inland from fluvial and marine flooding. Ecomorphodynamic systems evolve in time and space according to internal mechanisms that I tried to sketch with the diagrams before, but they also respond to external pressure. For instance, coastal dunes are squeezed from one side from urban sprawl, and from the other side from sea level rise. Similar also riverscapes are constrained by urban and crop sprawl, and also by climate change and changes in sediment supply, with the result that riverscapes changed a lot since the last century to nowadays. When answering to external pressures, ecomorphodynamic systems might lose their capability of providing ecosystem services. And this is why we actually need for conservation and restoration. And this is why these activities have been fostered and promoted by recent international initiatives or policy frameworks. And in those countries where conservation restoration has started to be applied, actually these activities has led to a flourishing industry. So this was just a general overview, but in practice, in the perspective of human and climate-induced changes, and also in the perspective of applying different management strategies or different restoration activities, generally we face two main challenges within ecomorphodynamic systems. First, we still need to completely understand the behavior in current conditions. And this means that the diagrams I showed before actually are not complete. They are only conceptual model, but we don't know what happens in reality or precisely. And of course, we can try to fill this gap by observation or by performing monitoring, but also monitoring raises additional questions like which kind of monitoring approach should we adopt? Should rely still on traditional field surveys? Should we move to more innovative methods? And the second challenge we face is strictly related to the first one, in the sense where we also needed to explore the response of ecomorphodynamic systems to alternative scenarios. And with alternative, I mean both new climate scenarios, but also management or restoration scenarios. And this is the field of modeling, of course, but in my experience, when we deal with ecomorphodynamic models, we face a challenge that is that generally the abiotic component of the systems, so all what regards topography, sediments, hydrology, or climate forcing, can be described in a representative way because we have a lot of data information. But all that regards the biotic component, for instance, vegetation, generally is described with uncertain parameters or arbitrary in its initial conditions. And so this leads to uncertainty about the results. So in my research, I look what was going on in other fields of the environmental sciences, and I saw that remote sensing was quite promising. So I tried to use remote sensing to bridge monitoring to modeling, in the sense that I try to set up monitoring strategies that are able to meet various requirements that might be cost, time, area requirements, while producing data that are compatible with models. And now I will show some examples. The first issue I have to deal with, also speaking in a chronological way, was studying riparian vegetation dynamics. Indeed, at the beginning of my PhD, I was asked to understand how riparian biomass changed over time. And so the issue was related to monitoring, but actually I was also asked then to model the behavior of riparian vegetation in different conditions, both using analytical models or numerical models. And both kinds of models require parameters to describe vegetation dynamics or the roughness, the resistance to water flow due to vegetation. So in this case, my requirements were to cover a large area. I started from a river reach, but I wanted potential having a solution for the entire river network, and having a multi-temporal information, and have information not only on vegetation, but also on topography, because I wanted to understand part of the ecomorphodynamic feedback, and I have a low to medium budget. So I looked at the different possibility of data that were available, and in the end, I decided to work with a LiDAR sensor mounted over aircraft. And this choice was driven by two facts. The first one is that LiDAR provides a three-dimensional point cloud that represents the ground, but also the vegetation, as you can see in this figure. And I think that this might be interesting to characterize the vegetation. And second, aircraft constitute a good compromise between aerial coverage and spatial resolution, and they also have an affordable cost. Then, once decided the kind of data, I looked at literature to understand which algorithms were available to process this data. And basically, I saw that the approaches could be grouped into two families. The first one is the area-based approach that you can see here in the middle panel. In this approach, the point cloud is used to define a canopy height model. So basically, it's a two-dimensional approach. And this approach is very useful when you have low resolution data, but its application in ecomorphodynamics might be limited. The second group of approaches was called individual tree-based or tree-centric. And I thought it might be more interesting with more potential for ecomorphodynamic applications because it leverages the whole three-dimensionality of the word cloud, the point cloud, because it works on the entire three-dimensionality of the cloud. Yes. And looking at the literature, I saw that for the first approach, first kind of approach, there are several open source algorithms that I could use. But for the second kind of approaches, the solutions that were available were not suitable for studying riparian corridors in temperate areas. So I had to develop a new one. I explain better this point. Generally, the available algorithms for the second kind of approach looked for detect individual trees by working on the canopy height model and detecting the local height maxima, as you can see here. And this method is very suitable in coniferous area where these methods have been developed. But if you applied in a temperate area where you have deciduous trees, so rounded shape found, the local height maxima are not univocal. So this method is not reliable anymore. So to find a solution, I started to analyze the LiDAR data I had. And in the end, I understood that for mature vegetation, the areal point density, if you squeeze all the cloud on the ground, the areal point density increases towards the plant center. So in my approach, I do not look for local height maxima, but for local maxima in the point density. So I set up an entire algorithm based on this assumption. And here you can see a workflow. Basically, it squeezes the cloud on the ground and then detects the local maximum point density. And then the algorithm applies some filters to remove double counted trees or anthropic objects. And in the end, the algorithm produces a map of the tree coordinates and tree height. I tested the performance of my algorithm and I was quite satisfied. But then I started to use it for practical purposes and I recognized that I missed a piece because the underlying assumption works very well for mature trees, but it's not valid anymore if you talk about shrubs or bushes. And in riparian corridors, we have a lot of shrubs or bushes. So I decided to extend my algorithm by producing an updated version. And starting from the previous one, so having a map of the mature vegetation, I added a module for masking shrubs and bushes based on RGB images, and then to segmentate the shrub areas, for instance, and then to clip the point cloud corresponding to shrubs and compute the volume of this part of vegetation. And so from one side, we have tree geometry from the previous algorithm, and from the other side, we have shrub geometry from this new component. And finally, the algorithm delivers a biomass map. Obviously, for moving from geometry, so volume and height, to biomass, we need the parameters. And the parameterization was based on the intensive food measurements that I carried out during the years. I tested this LiDAR-based mapping approach into areas. The first site is the Cinca River in Spain, where I had a low-resolution LiDAR dataset, and so I was able to apply only the area-based approach by using a commercial software, Fusion LTV. And the second area is the Orco River in Italy, where I had LiDAR surveys acquired in different periods, in particular 2019 and 2021, with a very good point resolution. And so it's where I was able to apply the tree-centric approach and develop my algorithms. And in both cases, the field campaign was an important part of the work. So the outcomes of the algorithms I set up were several. First, I was finally able to have maps of vegetation biomass, so understand what was happening over time. And you can see an example of vegetation biomass for some reaches of the Orco River in Italy in the first column of this figure. And second, by comparing biomass over time, I was also able to detect hotspots of measured change. For instance, in the second column, you can see reddish area that corresponds to extensive vegetation removal. And finally, since the LiDAR provides also information on topography, I was able to compare changes in biomass with changes in topography and understand what was going on from an ecomorphodynamic perspective. For instance, if we look at the second row, we understand that the removal was due to a sudden change in the flow direction. So from the monitoring side, I was satisfied, but then I tried also to apply these vegetation maps to inform models. I started from an analytical model. Here I reported the example of the model by Camporelli and Ridolfi. In this model, the behavior of vegetation biomass over time is described by two equations, one for decay and one for growth. And the switching between these two equations is due to water level fluctuations, so hydrological disturbance. And since hydrology is a stochastic process, the switching between the two equations is random, and they can be combined in a single stochastic differential equation, whose solution is not a deterministic value for the vegetation, but it's a probability density function of the vegetation biomass, as you can see here. And in this solution, there are some parameters that are related to topography or hydrology, and that can be computed by using available data or by performing hydrodynamic modeling. But there are also some parameters that are related to the biology, so like the decay or the growing factors. And this parameter needs calibration. So I calibrated them for several cases. Here I reported the example of the Cinca River in Spain, where relying on an area-based approach, I subdivided the study site into areas with equal probability of inundation, and then I calibrated the solution. After calibration, I tested over another site, of course, and then I used the calibrated model to inspect what might happen in the area if the hydrological condition changed. So I looked at the projection for the water flows in the area, and I saw that it was expected in the future. In the future, it's expected a dramatic reduction of the mean water flows with an increase of the standard deviation. And introducing these changes into the model results, so we can say the blue parameters in the probability density function I showed before, we saw that vegetation biomass will experience a dramatic reduction in the floodplain, as you can see in the last figure here. And the reduction is dramatic almost everywhere, except in some area where actually vegetation will experience a growth. And this is why this area in current condition are too much disturbed by inundation, but in the future they will find more suitable conditions. I also try to use the biomass maps I derived from my algorithm to set up numerical models. In this case, I needed the results from the tree-centric approach because I need information on individual plant geometry. And I used the that3D morphodynamic modeling suite coupled with a MATLAB or Python routine for describing vegetation dynamics. And I used the outcomes of my algorithm in 3 ways. In the first way, I used the geometry provided by algorithms to provide information about plant geometry, assign a roughness value to each computational cell. Then I also used the outcomes of the algorithm applied to the first LiDAR dataset I have, so 2019, to set up the initial scenario. And the information were extracted by the outcomes of my algorithms or by applying empirical models to it for those variables were not available. And finally, I used both the information from 2019 and 2021 to calibrate some growing and decay parameters. And it was an interesting work because after calibration, we were able to simulate different scenarios and different conditions. So that's all regarding the first application. And after working in riparian areas, I started to translate the approach to different conditions. So I started to study vegetated coastal dunes. I started from the literature, and I saw that there were actually very few works on this topic, so dealing with ecomorphodynamic modeling. And interestingly, these works generally refer to the same parameter, which is called LVEG in this figure, or beach width, or vegetation zonation. And this parameter describes the distance between the swash zone and the place where vegetation can establish and trigger dune formation. And as you can see in this figure, this parameter is quite important because it has a great influence on the final dune geometry or dune field geometry, and depends on environmental disturbances. However, this parameter is generally set arbitrarily in the models, while a realistic value might be useful to support understanding the actual space needed by the dune field, and for its pre-development and for providing ecosystem services. So in my research, I wonder, how can I provide this information to models? Obviously, working on a local scale, this information can be provided by field surveys or by inspecting orthophotos, as did here. But if you want to move to a global scale, it might be more challenging. So the requirements of this work were to work on a large area, possibly global, and having multi-temporal information and working with a low budget. So I thought that the most suitable solution would have been working with Earth observation products. And I looked at the literature to see existing algorithms, and I saw that there were a lot of Earth observation-based algorithms for detecting sand and shorelines. However, we also need the vegetation in order to detect the parameter. So I got in touch with the authors of one of these algorithms, in particular the right one, Eugene Dyke, and I started to collaborate with him and its group at the Deltares, and we improved this algorithm in order not only to classify sand, but also to detect two types of vegetation, and not only to detect the shorelines, but also to detect the so-called vegetation lines, so the interface between vegetation and sand. And we validated the model and the algorithm, and then we started to use it for several purposes. The first one, to understand from an ecological and morphological perspective what happened in several coastal areas, so to see the evolution over time. And also we started to use it to determine the LVEG parameters. And finally, I tried to use it to calibrate a ecomorphodynamic model for coastal vegetation. And here I reported the example of a model. It's very similar to the one I show for the riparian case. Actually, also in this case, the vegetation cover evolves over time. Evolves over time, decaying or growing according to the magnitude of external disturbance. In this case, the disturbance is due to both waves run-up, but also sand transport. Also in this case, the switching between the two conditions is stochastic, so the solution is a probability density function, but I will not report it here because it's quite complex. It's not the scope of this presentation. The interesting part is that I tried to calibrate this model by using Earth observation products. And I took several beaches along the US coast. And for all of these beaches, I tried to define an average topographical profile by sampling the available digital elevation model. And at the same time, I applied the algorithm I described before to obtain also an information on the LVEG, but also an information about the average vegetation cover profile over the beach dune system. And then I use this information to calibrate this model. And on the right part of this slide, I reported a couple just of examples of the calibration. And interesting, we saw that in some cases, the calibration was very good, and the calibrated model works very well. Indeed, for instance, in the upper panel, you can see that the model in blue resembles the results of the Earth-based algorithm. In particular, the yellow dots represent the algorithm applied to Sentinel-2 images, while the red one, the algorithm applied to PlanetScope images with a higher spatial resolution. In other cases, we saw that the calibration was not so satisfactory, and we thought that the gap might be due to the fact that we consider a single plant species instead of the gradient of species we have along the beach dune system. And the work is still under review, so maybe the reviewers have a different opinion, but we thought that this might be a reason. And this led directly to the third application I will talk today, which was detecting vegetation species in coastal areas. In this case, we changed a little bit our request, in the sense that we didn't want to investigate all the US coast, but we were okay with a narrower area, because we want to improve the spatial resolution of our analysis in order to be able to detect different species and potentially in a multi-temporal way. And we were also able to spend a little bit more. So the solution we developed was not based on Earth observation from a satellite anymore, but on drones. And we performed several field campaigns in the Migliarino San Rossore Massaciucoli Park in Italy, Tuscany. And then we set up a classification algorithm that works in a hierarchical way. Here you can see the results. At the first level of classification, the algorithms perform an object-based image analysis to detect individual plants and to segmentate individual plants. And then at the second level of classification, it assigns the plant species. And we are still exploiting the results because the work is quite recent, but having performed this kind of surveys for several years since 2021, I think we will find interesting results about species evolution over time. And also we are trying to understand how to use this output for a fine-tuning calibration of the model I presented before. Now I will just show very briefly, I will call very briefly what I'm doing here at CMCC, changing a little bit the topic. At CMCC, I'm working on soil erosion assessment, and I started to approach to this topic because it was asked by projects, of course, but also because soil erosion is a major threat nowadays, and it's exacerbated by climate change. So there's a continuous feedback between erosion, vegetation, and climate change, and I thought it's very interesting. And soil erosion has ecological impacts, of course, but also socio-economic impacts. And this is why it has raised the interest of policy, and policies have started to include the soil erosion indicators to assess the progress towards their goals. And this signs a gap, because from one side, the policy asks for indicators, but from the other side, the available soil erosion assessments are not periodic, generally have a coarse scale, and generally they are not reproducible because they are not open source. So at CMCC, we are trying to address all the requirements by the stakeholders of our project, which are covering a large scale from catchment to national scale, and providing assessments at a good spatial resolution with the time frequency and potentially with a short delivery time. And also we are asked to implement a precise model for soil erosion assessment, which is the revised universal soil loss equation, RASLE model, which you can see in this slide. And this model is quite simple, but it's widely adopted worldwide. And we were asked to implement it because it allows cross-comparison in time and space. We are working to this topic in several projects that you can see here. So the solutions are customized depending on the project, but generally all the proposed solutions we are developing are based on two aspects. The first is that we are trying to combine Earth observation products with different sources of data, for instance, in field or modeling outcomes. And also we are trying to using artificial neural network techniques or artificial intelligence techniques more in general to see if you can improve the assessment of the estimation of the factors contributing to soil erosion. Also, in our project, we are trying to refine some of the factors of the RASB model in order to account for infrastructures, which is something that has never been done before. For a matter of time, I will just show very briefly what we are doing regarding one of these factors, which is the land cover management. The work is still ongoing, but so I will show only some initial results. For this factor, generally, the assessment is carried out as annual average, and also it's based on existing land cover maps, for instance, Korean land cover. So the result is that if we rely on this traditional method, we don't have information that are very useful to understand which area are most susceptible and in which period of the year the susceptibility is higher. So in one of the project I'm contributing to, SDGIs, we developed a tool to understand, to compute the land cover management at a subannual scale. And in particular, we implemented an algorithm that is able to compute the C factor based on spectral properties, in particular NDVI. And here you can see some of the results. The tool provides both annual results. For instance, here you have the results for the old river basin in Romania for 2018 and 2022. And this allows us to understand if major changes occurred. For instance, in this case, we see that there was an increase of the C factor, probably due to deforestation in this area. But the tool also allows for subannual analysis. For instance, you have for 2018 here, winter, spring, summer, and autumn. And this is quite interesting because according to the period of the year, the susceptibility changes and the area to be more protected changes. In another project, we carried out a step forward. We not only looked at the variability of the C factor at the subannual scale, but also at the variability of the rainfall erosivity, which is the driving force of erosion. And in this way, we were able to detect not only the most critical areas, but also the most critical period of the year. For instance, here you can see the example from the Idice River in Italy, where we perform a monthly estimation of this factor. And by multiplying the C factor and the L factor, we saw that with respect to these two factors only, the most critical period of the year is September. So to conclude, in this presentation, I show how remote sensing can support monitoring and modeling both in riparian studies. And I think in my opinion, that the most important part of my research is to show how monitoring can be structured to be functional, not only to understanding ecomorphodynamic processes, but also to provide information for models. And regarding future steps, I'm very aware that remote sensing is an evolving science, so I'm always exploring new or alternative products. For instance, you might have noticed that I never used radar data, but I'm starting to look in this direction. And also in some projects, I'm starting to understand how to use a super resolution multispectral images to detect some territorial features, for instance, terraces or stone walls that you can see here. Because these features impact sediment erosion, sediment detection and transport, but are generally not detected with the satellite images that are currently available. Regarding my interest in modeling, actually, so far I work in this different part of the source to sea system. So I work a little bit on the riparian part, a little bit on the coastal part. But in the future, I would like to work on the integration of these ecomorphodynamics the integration of this part in a unique ecomorphodynamic modeling chain. So that's all, and thank you for your attention.
Yeah, thank you, Melissa. Thank you so much for your presentation. I mean, you provided details for, let's say, a wide array of case studies and tools. It was a really, I mean, it was really articulated. So just to provide some guidelines to our participant, to pose some question for getting more detailed clarification from Elisa, please use the Q&A session within the Zoom. I can break the ice. I have several questions. As you know, I'm particularly engaged in adaptation planning, mainstreaming nature-based solution, and in this setting, I'm particularly interested in the European nature restoration law that is creating, I will say, a lot of opportunities for us as researchers and for investigating and providing support into climate change adaptation planning. In this setting, as you know, the natural restoration law required the development and implementation of monitoring plans for restoration activities and measures. So you presented a wide array of modeling approaches, remote sensing techniques. So how do you see the use of remote sensing in this context? And what are the potential for future development investigation?
Okay, thank you for the question. Yeah, actually, not only the natural restoration law asked for monitoring, but this was asked also by previous framework directive, for instance, the Water Framework Directive, sorry. And in general, you can see that from one side, policy asks for something, but in practice, in restoration projects, monitoring is not has not been implemented so far. So in the literature, there are several examples of statistics about monitoring implementation in restoration projects, and you can see that only a very small percentage of projects use it. And in general, in the project, monitoring is not carried out following standard procedures. So the comparability of data is hampered. So I think that in this sense, remote sensing can be very useful because from one side, you can customize your solution because remote sensing involves several techniques. And from the other side, you can create a monitoring plan that can be repeatable over time and space. So you can select the input data you want to use and the process, the algorithms you want to adopt in a standardized way, which is something that has not done so far. And I think that also remote sensing is interesting because now it provides solution for monitoring different components of the potentially restored system. For instance, you can use LiDAR data or SAR to monitor morphological changes. You can use, as I showed today, multispectral or LiDAR for the biological component. And you can use, for instance, multispectral maybe for water quality. So you can address the different targets or restoration, and you can potentially set up monitoring strategies that covers all the aspects. So you can really you can assess baseline conditions, and then you can really track the progress of the restoration. So I hope this answered.
Yeah, sure. Also because, I mean, you're perfectly right. I mean, there are other European directives that are asking to implement continuous monitoring, as you say, the Water Framework Directive and also the Marine Strategy Framework Directive, which pose other challenges that are related to the application of remote sensing within, let's say, for instance, marine space. So an evaluation of water quality parameters that, you know, that is also the area of my investigation. In the first application, you showcase the development of an algorithm. Do you think that the algorithm that you develop can be generalized, it can be flexible enough to be applied to other case studies?
Okay, I developed this algorithm specifically for temperate areas because in this area, the underlying assumption regarding the point density holds. And I think that the domain of application should be restricted for this area because, for instance, I never tried in tropical areas, but I think that in these cases, the vegetation is so dense that maybe the underlying assumption does not hold anymore. So it will require the additional test, we can say, for the domain. And then in practice, I provide some parameters to pass from geometries of vegetation to biomass. And for these parameters, I perform field surveys. And so a potential user can use the parameter I provide, but for be more precise, it should perform additional field campaigns. So maybe the generalization is constrained by the availability or possibility to integrate the analysis with some field investigation.
This was a question that also emerged in the Q&A session. There was Anna Maria Mazzoni asking right to the, let's say, how the tool can be easily applied in other, transferred to other region, other case studies, which are the key factor that enable the replicability, but also the barrier, the constraints. So as you say, maybe you may need further investigation fieldwork to adjust the parameter, right?
Yeah. Exactly. And actually, my algorithm was applied by all the other researchers as well. And in some cases, they use the default parameters, but they use it only to perform cross comparison over time. So maybe the absolute value of parameter was not so impacting, but in other cases, they perform field surveys in order to have more representative results.
Connecting to the fieldwork activity that you mentioned, you presented a coastal case study. What field activities did you carry out within this case study?
Okay, the case study was in the Migliarino San Rossore Park in Italy. And first of all, I have to say that we selected the area because of its feature, because it was easily accessible I was at the University of Polytechnic of Turin in that time. So it was easily accessible. And it allows us to go there with all our equipment for field surveys. So we were 4 to 6 people each time. We were there several times. And each time you perform drone acquisition with a multispectral and a LiDAR sensor. So 2 people were doing that. Other people were performing ground surveys. In particular, we measured a lot of plants for each species. So for each sample, we take the coordinates and we assign the plant species. And this was a very demanding work because we have, I think, 20 plant species, and we took at least 100 of samples for each species. And the field campaign were related to a wider ecomorphodynamic investigation. So we also perform additional measurements regarding the bathymetry. So we have a multi-beam mounted over a boat, and we also perform some measurements on the dead wood on the beach. Yeah,
well,
it was a lot.
I will say that the field work was, it was very articulated.
For my algorithm, I only use the data by the drones and by the field detection of the plant.
Okay, but all the other activities were very articulated from what I understood. In the last case study, you talk about soil erosion and the equation that you applied. I took some notes. You consider integrating information on rainfall, erosivity, slopes, soil erodibility, land cover, support practice, and you were saying that you didn't integrate infrastructure, if I understood correctly. So is it a topic of future investigation?
No, we are starting to integrate this aspect because in the current assessment of soil erosion, anthropic objects like transport network is not included. But we thought it is important because in reality, it impacts on the soil erosion budget. So for instance, we modify the parameters, the factor related to morphology, the slope and stiffness factors. And we started from a state-of-the-art algorithms, and we added a function to upload the shape files of the road network, for instance, and to modify the digital elevation model according to that. Also, in other projects, we are, as I mentioned in the last slide, we are trying to use very high resolution satellite images processed with a super resolution algorithm in order to detect, for instance, terraces, or to find a finer detection of the transport network. In order to understand it from this information, we can correct a little bit the budget of erosion.
So it's something that you're already developing an ongoing project. So it's not for, let's say, okay, that sounds good.
So ongoing.
And maybe a tricky question, because at the end you say that in your future research you aim to integrate all these different parts that you present in the modeling approaches. And I was thinking also to one of the first slides, the second slide that you presented with the ecosystem services flow against the source to sea dimension. So, and I was wondering that basically you started with this big, amazing research question. And then at the end you say that you would like to put together all the pieces of the puzzle. So I would say that it will allow to respond also to this source to sea approach. So how do you see this modeling approach, this chained modeling approach is evolving in your research?
This is a very tricky question. I don't know. I think I would like to start working in existing models, modeling change that already accounts for different parts of the systems, and then to see if, in particular, some components of this model already integrate all the actors of the ecomorphodynamic feedback. We can say to understand if, for instance, the erosion part already takes into account vegetation and so on. So I think I will start working piece by piece, but into already existing modeling chain, because otherwise it would be very challenging.
Yeah,
and
otherwise
then
can
once
be
you have
quite
everything
challenging.
set up, yeah, exactly, you can perform analysis, for instance, about ecosystem services, so future impact of different climate conditions, for instance.
Yeah, because this connection was particularly relevant for also designing adaptation measures that are able to, let's say, to provide multifaceted ecosystem services and, let's say, be applied under a, let's say, cross and integrated approach in adaptation planning.
Yeah, and I think that having a source to see perspective is very important with this respect, because if you design maybe adaptation or mitigation strategies, for instance, in a coastal area without knowing or understanding what will happen from inland, it could be that your solution will not be so effective in the near future. So I think the whole picture is very important.
Yeah.
Challenging,
This is
but
why I would say,
important.
yeah, challenging, but for sure it's important within also the big umbrella of the mission adaptation that is targeting this achieving 150 regions in their climate resilience, so having a more structured approach into climate adaptation planning and systemic and cross systems approach is prominent. No other question in the Q&A session, so I will say that we are reaching the end of this webinar. So as a first, Melissa, thank you so much for all the details that you provided us, the information on the ecomorphodynamic system, but especially, it was, challenging for you to present all this wide array of tools and case studies.
Following everything, but yeah.
No, but I do believe that you gave us a lot of knowledge and a great opportunity also to brainstorm, let's say, on ourselves and identify some other areas for future investigation. So I really thank you, because it was inspiring, honestly, this webinar.
Thank you very much.
I thank also all participants to the webinar for the question and also the engagement during the discussion. So I will say that, as I say, it was a prominent topic for future investigation and collaboration. So let's keep the conversation ongoing and open beyond this webinar. So stay tuned and see you to the next CMCC webinar. Thank you. Thank you so much. Have a great day.
Thank you. Bye.
Bye.